Hey everyone, today we're going to be talking about absolute and local maximum and minimum. Now, before we get into kind of the nitty-gritty details of the definitions of these things, I want to give you guys a broader sense of what these terms are supposed to capture in your mind, right? Sort of the intuitive notion that they try to formalize. So imagine that this curve here, representing some function, is a mountain, and that you, represented by a stick figure, are taking a hike on this mountain. So you're descending down from a high point on the mountain into this valley. Keep going down, down. You reach this sort of valley here, this bottoming out point, which I'm going to mark. And you start climbing again. Your hike turns upward. You keep climbing for a little bit until you crest the top of this hill. This gentle little slope here. And you start going down again. You start descending the mountain. After some more descent, you reach another valley, this one a fair bit deeper. Turn up again, because you've reached the bottom and now want to go up. Climb up another hill, reach the top. Go down. Another valley. And finally, start climbing up off to the right in the distance again. Now, let's say you get home after this long hike, and you're telling your friend about it. And your friend is not quite as avid a hiker as you, and he says, I'm interested in hiking this mountain too, but I'm only interested in this little part of the hike, right? Represented on the curve as the part between x equals -2 and x equals 6. And your friend says, I want to know what's the lowest elevation you got to on this part of the hike that I'm interested in, and what's the highest? And so you break out your map and you say, well, along this part of the hike that you're interested in, the lowest you get is right about here, and you get to about an elevation of -1 below sea level. And the highest you get is way off to the right at the very edge of this part of the hike you're interested in. It's off over here, and your elevation is about 1.75 above sea level. And then suppose your friend asks, well, okay, so that's the top and the bottom. How are we getting between there, right? How does the hike look like in between? Do we kind of take a straight shot up? Or is it more bumpy? Is there more up and down? And well, you could point to the map and say, well, first, we went up, and then we crested a hill right up here, and we changed direction once, go down to a valley, and change direction again to finally reach the maximum point. And notice that these turning points, they're kind of the tallest or lowest thing around. If you look in a little area around them, this little top of the hill, it's the highest point in that little region. And if you look in a little area around this other turning point, this little valley, the valley bottom is the lowest point around, right? Sort of locally, it's the smallest thing. These are the concepts that the definition of maximum and minimum try to capture, being the tallest or lowest thing around. So, moving on to definitions. The absolute maximum or minimum points of a function in a particular interval are the points where that function reaches its largest or smallest value, depending on whether you're talking about maximum or minimum, in that interval. So in that interval your friend sketched out, -2 to 6, the absolute maximum would be up here at the point 6, 1.75, and the minimum would be right here at the point about -1.75, -1. Now a local minimum or maximum point of a function is a point that can be an absolute minimum or maximum if you look at a small enough open interval. So, intuitively speaking, once you narrow your field of view small enough, the point you're looking at becomes the highest or lowest point around. So for this top of the hill here, if we narrow our field of view to the highlighted area, the top of the hill becomes the highest thing around, right? Same here for the rightmost valley. If you narrow your field of view enough, the bottom of that valley becomes the lowest point around. And for the leftmost valley, same deal. If you narrow your field of view, it becomes the bottom, or the lowest thing that you see. Now the reason the definition specifies that it has to be an open interval is that if we expanded the definition to allow closed intervals, we could make pretty much any point a local maximum or minimum just by having it being an endpoint on an interval. For example, if I chose this closed interval here, the endpoints, the right endpoint would be a max point on that closed interval, and the left point would be a min point on that closed interval. And we don't want that, right? We don't want our definition to include these middle points on the slope of this mountain, because those don't really capture anything meaningful. They don't capture the turningness of the function like these crests and valleys of the hill, crests of hills and bottoms of valleys do. But in any case, the local minima happen at about minus 1.75 minus 1, so the same as that global minima from before. The one here is about 1.8, 1, and the one here is at a horizontal distance of about 4.25 and a height of just about 0.25. Now, if we're talking beyond that little portion of the hike that your friend was describing, minus 2 to 6, and start talking about the entire hike, which we think of as going from minus infinity to infinity, our minimum point doesn't change. The bottom of the hike is still that bottom of the deep, deep valley at minus 1.75, minus 1. But our maximum point changes. In fact, we have no maximum point because this mountain kind of shoots off into infinity on both sides. So this function has no absolute maximum across its entire domain, the entire real numbers. So no maximum. Notably though, if we widen our field of view that much, we find two more local minimum and maximum, which I'm circling in purple right now. There's the one at about minus 7 horizontal distance and about a height of 1.5. And there's one here at a horizontal distance of just about minus 5 and a height of maybe 1.9. So to our local minima, we're going to add minus 7, 1.5, and minus 5, 1.9. Now, it turns out that this definition here of local min and max exactly describes these turning points when your function is a smooth curve with no breaks, right? If you have a smooth curve with no breaks, you can think of this definition up here, this more abstract definition, as just meaning turning points, right? Tops of hills, bottoms of valleys. It's a pretty simple way to interpret it. However, when your function isn't a smooth curve with no breaks, when it's not continuous and defined, you have to be a little bit more careful about what you're calling your local min and max. So I'm going to show that off a little bit in my second example. with a function that definitely isn't unbroken and smooth. You know, it's got these weird isolated points. It's got break here, and it's got a vertical asymptote here. But despite that, despite the fact that this function looks nothing like any mountain that I hope you've ever tried to hike, we can still ask about the local min and max on various intervals, starting with this one, from -infinity to -5. From -infinity to -5, the highest points around on the function are these isolated points here, right? They're all the same height, so all of them are maximum points. And they have horizontal distances of -9, -8, and -7 respectively, and their heights are all 1. So we're going to write those 3 points as -9, 1, -8, 1, and -7, 1. The lowest point we reach is on the very right. It's at a horizontal distance of -5, and its vertical distance, we'll say, is about -0.2. And there's only one of them, because we only reach it on the very right. Now, if we were to look at the second interval here, -2 to 2, represented on the function as this little area, we see that we have neither an absolute minimum or maximum, because on the maximum side, our function shoots way off unboundedly, off to infinity, and on the minimum side, it also shoots way down off to unboundedly small, right? Negative infinity, you can think of it as. So on this interval, the function has no max or min. Finally, we're going to look at the open interval, -5 to 0, represented by this little area here. And at a first glance, we might be tempted to say that the maximum point is at the very edge of the interval, right? Just at x equals 0, right there. But we have to remember that that point isn't actually contained in our open interval, right? The open interval has all the points less than that, but not that endpoint specifically. And that means that our function actually has no absolute maximum on this open interval, because no matter how close we try and pick a point to that endpoint, say we pick it right about here, there's always going to be points that are even closer, right? You can't pick any point that's bigger than, that reaches a higher height than every other point, because you can always nudge just a tiny bit closer past any point you pick. So on this interval, there is no maximum. But the minimum happens right around this little dip right here, at about a horizontal distance of -4 and a height of, we'll say, about -0.25. As for local minima and maxima, we first have this leftmost isolated point here, which is actually both a local minimum and a local maximum, because if you draw a little open interval right about here, that isolated point is both the highest and the lowest point around, because it's the only point around. So this point here, -9, 1, is both a local maximum and a local minimum. And the same goes for these other 3 isolated points, because you can narrow your field of view so much that they're the only point around. So -8, 1, -7, height of 1. And as before, this bottom of valley here, which we saw was at -4, height of -0.25, is still a local minimum, just because it's the bottom of a valley, and there's this little region around here where it's the smallest thing around. And finally, this top of a cliff here is also a local maximum because if you narrow your field of view to around here, it's the highest thing around. So that's at 0 with a height of about 1.25. And those would be our local maxima and minima. You might be tempted to call this point a local maximum or minimum, also because it looks like it's isolated. But notice that if you try and draw a little region around it, you start capturing bits of the asymptotes here, right? This little bit that shoots off to infinity, and this little bit of the graph that shoots down to minus infinity. So that point, even though it kind of looks like the isolated points on the very left, is not quite the same. Now I want to leave you guys off with one last interval to think about, and that is the interval starting at 5, including 5, that goes all the way off, or it goes all the way off to infinity, so it includes the entire right half of the function, essentially. And I want you to think about whether this function has an absolute minimum or maximum on this interval where it seems to be asymptotically approaching 0. But otherwise, that has been absolute and local maximum and minimum. Hope you guys found this video helpful, and see you in the next one.